In this video, we are going to learn how to evaluate double integrals using a change of variables. In order to do that, we are going to need the tools we learned about in the previous video, which are transformations and the Jacobian. So our goal is to generalize the substitution method of integration to double integrals, or our U substitution. In order to do so, we must determine how a substitution will affect the area element dA. Right, that's one of the important pieces when we're using a change of variables for double integration. Now, in order to do our double integration, let's first look at a U substitution for a single integral. So we have the integral from 1 to 6 of the square root of 5x minus 1 dx. So going through a formal U substitution, the function that's inside of the square root, which is 5x minus 1, we will define as U. du is then 5 dx, and 1/5 du equals dx. Now, normally, we typically contain this all within the integration. We haven't really written out many formal U substitutions as we've proceeded through our double and triple integration, but this is what it would look like as a formal U substitution. Now we need to convert the integral. So this is going to be equal to the integral of the square root of u times 1/5 du, replacing the dx with the du element we found here. And then we have to change our bounds of integration. So if x was 1, then u equals 5x minus 1, so u equals 5 minus 1, or u equals 4. And if x were 6, u equals 30 minus 1, u equals 29. So our lower bound is 4, our upper bound is 29. So converting the bounds, that's going to be where the transformation helps us for our double integration. Right, we're going to figure out how the bounds on a dy dx or dx dy double integral will map to the uv plane. And then the scale factor, that's where the Jacobian is going to come in. If we compare here, the interval we're integrating with respect to u is 5 times the length of the interval we're integrating over with respect to x. And the 1/5 accounts for that difference in the length of the intervals. And if you remember how we defined the Jacobian, that was the scale factor between the areas in the uv plane and the xy plane. So that's how we're going to account for the difference in the area that we're integrating over. So let's see how all that comes together. So suppose that T is a C1 invertible transformation that maps a region S in the UV plane to a region R in the XY plane, and whose Jacobian is non-zero. Remember, C1 just means we have continuous first-order partial derivatives. If T is defined as the transformation x equals g of uv, y equals h of uv, then we can redefine the double integral over the region R of our function f of xy dA over the area element as the double integral over the region S, redefine our function in terms of u and v, so g of uv, h of uv for x and y respectively. Then our Jacobian, so that's the partial notation there. And remember, more informally, we just wrote this as j of uv. I'm fine with either. This is just the more formal approach there. And then du dv. So this whole piece here, that's your area element. So you have the Jacobian to account for the difference in the area, and then the du dv because we're on the uv plane. And then we have our function redefined in terms of u and v, same way we did for polar, cylindrical, spherical, and we're integrating over the region S. So note that we use the absolute value, so that's something you might want to highlight there, of the Jacobian determinant in the integration formula above, as area is always positive. So remember, a negative Jacobian just told us that there's some rotational element to the mapping, but for our purposes with our double integrals, we're really focused on just the area part of the Jacobian, so we want to make sure we take the absolute value of any negative Jacobian we get. All right, a couple of guidelines, insights to help us through a change of variables for a double integral. We want to identify or create an invertible transformation, right? That's our first step. So hopefully they give it to us, then we're just identifying what it is, and if not, we have to create our own. Determine what the region S in the UV plane looks like so that we can figure out our bounds of integration. Find the Jacobian determinant because we're going to need to put that in to our double integral. Then define the double integral in terms of u and v, so do the actual substitution. Don't forget about that absolute value of the Jacobian, and then we integrate. All right, so this is good to look back to if you ever are forgetting a step in the process. So our first example, use the transformation x equals 2u minus v, y equals u plus v to evaluate. So this right here, that's our transformation. That's our t. So we've identified the transformation. Then we're trying to evaluate the double integral over the region R of x plus 2y dA, where R is the region bounded by y equals 1/2 x, y equals 2x, and y equals 3 minus x. So now that we have the transformation, let's figure out what the region looks like in the UV plane. So we have y equals 1/2 x to start. So very simply, we substitute the transformation in. So u plus v equals 1/2 2u minus v. Probably easier to multiply both sides by 2. So 2u plus 2v equals 2u minus v. The u terms can simplify, so then we get 3v equals 0 or v equals 0. So there's our first curve in the UV plane. Next up, we have y equals 2x. So same idea. So we have u plus v equals 2 times 2u minus v. U plus v equals 4u minus 2v. So then we get 3v equals 3u, or v equals u. And then lastly, we have y equals 3 minus x. So that's going to be u plus v equals 3 minus 2u minus v. So u plus v equals 3 minus 2u plus v. The v terms simplify here. So 3u equals 3, u equals 1. Right, not the fastest process, but just a matter of going through, plugging the transformations in, simplifying to get curves in the UV plane. So if we drew this in the UV plane, we get v equals 0, we get u equals 1, v equals 0, and u equals v. So here is our region S in the UV plane. Next up, we need our Jacobian. So x and y are defined in terms of u and v, so our Jacobian is also in terms of u and v. And that's relevant because we will be dealing with inverse transformations as well. So partial of x with respect to u is 2, partial of x with respect to v is -1, partial of y with respect to u is 1, partial of y with respect to v is also 1. So our Jacobian is 2 plus 1, which is 3. So now we can take all this information and set up our double integral. So we have the double integral of x plus 2y. So that's going to be x, 2u minus v, plus 2y, so 2u plus 2v, Jacobian. And then as far as dv du or du dv, we have to decide whether we want to define the region as a type 1 or a type 2 region. So I think it's simpler as a type 1 region, but doesn't really make too much of a difference. So we're going to go dv du. V goes from 0 to u, and u goes from 0 to 1. So if we simplify, we can say this is the double integral from 0 to u, 0 to 1, of 4u times 3, so 12u, and then plus v, so plus 3v, dv du. I'm going to save some integration here. I don't think this is the most challenging integration that you've been doing recently. So I will give you the answer, which is 9/2. And you can always practice your integration and confirm you get that value out. But really the more important part in this example is the process. Transformation, finding that region S in the UV plane, finding the Jacobian, and putting all those elements together in a double integral. Our next example, use the transformation x equals u over v, y equals v to evaluate the double integral over the region R of xy dA, where R is the region bounded by y equals x, y equals 4x, xy equals 1, and xy equals 4. So, first thing, identifying there's our transformation. And we have to use that transformation to redefine all four curves. So start with y equals x. So that means v equals u over v. V squared equals u. Y equals 4x. So v equals 4 times u over v. V squared equals 4u. And I'm not going to go past this as far as moving the 4 over because we need to decide whether we want to solve for u or v here, which is really going to be dictated by the next two equations. So xy equals 1, so that's u over v times v equals 1, which is u equals 1. And xy equals 4 will be u over v times v equals 4, u equals 4. So because the bounds of u are constant, that means we want to solve these two equations for v. So v equals the positive square root of u, v equals the positive square root of 4u, so that's going to be 2 square root of u. And I guess they didn't specify, but we can add here R is the region, we could say, in the first quadrant. Right, just to be more specific, that piece of information would probably be added in. So we're in the first quadrant, so that's how we know that we want the positive square roots there. U equals 1, u equals 4. So now we have our curves on the UV plane. Okay, so u, v. So we have v equals the square root of u. V equals 2 times the square root of u. U equals 1. And u equals 4. So our region S is right in there. Now, is this the simplest region? Is it a rectangle like we hope, or a simpler triangle? No, but it's still simpler than the region that we would have had to define on the xy plane. And go ahead, graph it. There's 2 hyperbolas and 2 lines, and if you graph it, you can pretty quickly see that it would be difficult to define it as either a type 1 or a type 2 region. So now we have our region. Next up is our Jacobian. So the Jacobian in terms of u and v. Okay, so x is u over v, so the partial of x with respect to u is 1 over v. Partial of x with respect to v is negative u over v squared. And then y is v, so the partial of y with respect to u is 0, and with respect to v is 1. So taking the determinant of that 2 by 2 matrix, we just get 1 over v as our Jacobian. So this is another important thing to highlight, is the Jacobian doesn't always have to be a constant. Right? We saw that with the polar. Right? The Jacobian of the polar conversion is r. Right? So sometimes our Jacobian will be in terms of a variable that we're integrating with respect to. So now we want to set up. So again, I do think type 1 region makes more sense in this example. So we have our double integral. What are we integrating again? We're integrating xy. So that's going to be u over v times v. Then our Jacobian, 1 over v. And then as a type 1 region, we're going dv. Let's erase that. It almost looked like a u. We don't want that to happen. So dv du. So v goes from the square root of u to 2 times the square root of u, and then from 1 to 4. Right, inside those v's will simplify. And let's go to the next slide. Let's actually integrate this one because there is something that happens that I want to take a look at. So integrating with respect to v here, we have the integral from 1 to 4 of u times the natural log of v, evaluated from the square root of u to 2 square root of u du. So this is equal to the integral from 1 to 4 of u natural log of 2 square root of u minus u times natural log of the square root of u du. Okay, so we can write that as the integral from 1 to 4 of u, factoring out a u. And then if you remember, subtracting log terms is really division of what's inside. Right, so we do need some log rules here. So that's natural log of 2 square root of u over the square root of u. And without it, we would just leave ourselves in a really difficult spot to integrate. It could be done, but it would be way more challenging. Now, if you look at that simplification with our log rules, the square root of u terms would simplify. And really what we're left with is the integral from 1 to 4 of u times the natural log of 2 du, which is a much simpler integral to evaluate. So then we just get 1/2 u squared times the natural log of 2. Evaluate that from 1 to 4. So we'd have natural log of 2 over 2 times 16 minus 1. So that's going to be 15 natural log of 2 over 2. Right, and that was all down to that log rule simplification that helped us out with our integration. Okay, so that's what I want to take a look at in this particular example. Next, evaluate the double integral over the region R of x minus y over 3x plus 2i dA, where R is the region bounded by 3x plus 2i equals 1, 3x plus 2i equals 4, y equals x minus 1, and y equals x minus 3. So the first thing that might stand out to you is they don't tell us what the transformation is. So in this case, we need to create an inverse transformation in order to do this problem. So we have to put in some effort to create that transformation. Okay, if we look at both the function that we're integrating and the curves, and here we might need to manipulate. So this one, probably better to write 1 equals x minus y and 3 equals x minus y. What you might start to notice is there's 3x plus 2y in the problem. There's x minus y in the problem. So defining u and v as 3x plus 2i and x minus y respectively would make for an easy transformation. So our inverse transformation then, we're going to say that u equals 3x plus 2y and v equals x minus y. So converting the sides, well then we have u equals 1, u equals 4, and then v equals 1, and v equals 3. So figuring out what this region looks like in the UV plane under this inverse transformation is actually easier than the way it was working previously. So we have on the UV plane, u is going from 1 to 4, v is going from 1 to 3, and we have a rectangular region, S, that we're integrating over. Now for the Jacobian, remember we need the Jacobian of u and v. The way we can find it, two different approaches. We can either solve for the original transformation, so we can solve for x and y using the inverse transformation and then find the Jacobian, or if we remember that second fact, we can find the Jacobian of the inverse transformation and reciprocate because of that fact that the product of the two Jacobians should equal 1. So let's use that second option. So we're going to find the Jacobian in terms of x and y. again, just a reminder, u and v are both defined in terms of x and y, so will the Jacobian. So partial of u with respect to x now is 3. Partial of u with respect to y is 2. Partial of v with respect to x is 1. And partial of v with respect to y is negative 1. So we have negative 3 minus 2, which is negative 5. So that tells us the Jacobian in terms of u and v is negative 1/5. Now remember, we do want to take an absolute value as we set up our double integral. So we're going to take the double integral of, let's remind ourselves, x minus y over 3x plus 2y. So that's v over u. V over u. And then we have times positive 1/5, right? It's the absolute value. And then for the rectangular region, doesn't matter the order, so we can say du dv. So u goes from 1 to 4, v goes from 1 to 3. And in this case, the integration really not too consequential, so we can do it out. So we can separate here. That's the nice part about both the function and the region. So we'd have 1/5 times the integral from 1 to 3 of v dv times the integral from 1 to 4 of 1 over u du. So this is going to be 1/5 times 1/2 v squared from 1 to 3 times natural log of u from 1 to 4. So that's going to be equal to 1/5 times 1/2, 9 minus 1, times natural log of 4 minus natural log of 1, which is 0. So let's see, we have 8 times 1/2, so that's 4. So we have 4 over 5 natural log of 4. All right, so that one was worth doing, as it wasn't really too long once we got to the stage of integrating in terms of u and v. And that's the hope, right? Really the hope is through this whole process, through all these steps, you get a double integral that's easy enough to integrate. Our last example, find the area of the ellipse 16x squared plus 9y squared equals 144. So again, we're not given a transformation, so we need to create an inverse transformation and then work from there. So really we want this to be a circular region over an elliptic region. So let's start to manipulate our equation. So if we divide both sides by 144, that's x squared over 9 plus y squared over 16 equals 1. And rewriting that as x over 3 squared plus y over 4 squared equals 1. So then we can define the inverse transformation. Make that look a little cleaner. We can define the inverse transformation as u equals x over 3, v equals y over 4, because then in the uv plane, this is going to be u squared plus v squared equals 1. Right, so if we were to draw our region in the uv plane, we're going to draw a circle of radius 1, and that's our region S. Okay, so we now know what the region looks like in the UV plane. We have our inverse transformation. So again, we have two choices. We can find the Jacobian of the inverse transformation and then reciprocate. Or in this case, just to offer a second approach, these two transformations are actually easy to solve. So if this is our inverse transformation, then our transformation going in the other direction would be x equals 3u and y equals 4v. So if we use this, we are just finding the Jacobian in terms of u and v directly with our transformation. So partial of x with respect to u is 3, with respect to v is 0. Partial of y with respect to u is 0, and with respect to v is 4. So the Jacobian is 12. Had you chosen to do the Jacobian of the inverse transformation, you would have gotten 1/12, and then reciprocating would give you the 12 that we got here. So setting up in the UV plane, we have the double integral area is just 1, and then times the Jacobian of 12 du dv. I'm just going to write s here. Now, when you look at the region in the UV plane, it would make way more sense to define in terms of polar because it's a circular region. That means you really need to do another change of variables. Now here that can be avoided, but I'll show both ways. So here, we actually don't have to do any integration at all. If we factor out the 12, double integral over the region S of 1 du dv, this piece here is just area. So the area of the circle of radius 1 is just pi. So 12 times pi, which is 12 pi. Now, had we wanted to actually integrate or needed to integrate, say this function was not just 1, then you would go to polar. Right? So we can say convert to polar. So that would be the double integral of 12r dr d theta. And now u would be r cos theta, v would be r sine theta if we needed that. And then in this case, we're going 0 to 1, 0 to 2 pi. And when you integrate this out, again, you should see that you get 12 pi. So I'm only offering the second approach because not every problem that's integrating over an ellipse is going to be an area problem. Sometimes we're going to have a function that we have to integrate over an elliptic region, and we're going to have to take this step of doing a conversion to polar, which, just to kind of bring it full circle, that actually means that we're doing 2 change of variables in one problem. So we dealt with transformations, inverse transformations. The Jacobian is a really important part for you to remember to get into that double integral. There are examples that are definitely way harder than the 4 that we covered here, but these are a really good starting point. With that, go practice, and I'll see you in the next video.